exoplanets. In the quiet depths of the night sky, countless stars shimmer like grains of light scattered across an endless ocean. Each one appears as a simple point, far too distant for the human eye to discern any details. For most of history, these stars were thought to be merely distant suns, glowing alone in the cosmic dark. We wondered about them, told stories about them, gave them names that carried through generations. But for thousands of years, we did not truly know what might exist beyond our own solar system. Whether there were other worlds circling those faraway stars, or if our home was uniquely blessed with planets, oceans, and the delicate chemistry that allows life to emerge. The idea of other worlds, exoplanets, began as a dream, a whisper of possibility.
Philosophers in ancient Greece and early astronomers from across the world speculated that the universe could be full of other Earths hidden from view. Yet, until the late 20th century, we had no proof. The night sky, though filled with stars, revealed nothing more than light. The distances were immense, the stars so bright that any orbiting planet would be lost in their glare. For centuries, the question lingered unanswered. Are we alone in the galaxy, or are there countless other planets drifting silently around other suns? As our instruments grew more sensitive, the dream began to take shape. The first clues arrived not through images, but through mathematics and motion, the subtle dance of gravity itself. When a planet orbits a star, it doesn't simply circle in silence. It pulls on its parent star ever so slightly.
The star wobbles, imperceptibly to the human eye, but measurable through the delicate shifts in its light. These faint tugs became the language through which astronomers first heard the whispers of distant worlds. In 1992, the universe answered our question. Two astronomers, Alexander Wolszczyn and Dale Frail, observed a pulsar, a rapidly spinning neutron star left behind after a supernova explosion, and detected regular changes in its radio signals. These variations revealed the gravitational influence of orbiting planets. They were strange worlds, circling the dead remains of a star that had once shone brightly. It was an unexpected place to find planets, but it proved something profound. Worlds could exist beyond our Sun. Just 3 years later, in 1995, another discovery would change astronomy forever. Michel Mayor and Didier Queloz announced the detection of a planet orbiting a Sun-like star called 51 Pegasi. This planet, later named 51 Pegasi b, was unlike anything in our solar system. It was a gas giant, roughly half the mass of Jupiter, but it orbited its star in just over 4 days, so close that its atmosphere was blisteringly hot. The world defied our expectations. We had imagined other solar systems as versions of our own, rocky inner planets, gas giants further out. Instead, the first confirmed exoplanet around a normal star was something entirely new. A hot Jupiter, a planet that showed us the diversity and unpredictability of planetary formation. From that moment on, the search for exoplanets became one of the defining quests of modern astronomy. New telescopes, both on Earth and in space, began scanning the skies for the faintest signs of planets orbiting distant suns.
Techniques evolved from measuring the wobble of a star to detecting the tiny dimming of starlight as a planet passed in front of it. This latter method, called the transit method, became the most powerful tool of all. It allowed astronomers to not only detect planets, but to estimate their sizes, their orbits, and sometimes even the composition of their atmospheres. The night sky, once thought to hold only stars, revealed itself as a vast gallery of planetary systems.
Every few weeks, new worlds were announced, strange, varied, and beautiful in their differences. Some orbited binary stars, dancing between two suns. Some skimmed so close to their stars that their dayside temperatures could melt metal. Others drifted in the cold dark, rogue planets without a home star at all, wandering through interstellar space. Each discovery expanded our understanding of what a planet could be. No longer were we confined to the narrow example of our own solar system. There were super-Earths, larger and heavier than our planet, with thick atmospheres that might hold oceans of vapor. There were many Neptunes, icy worlds cloaked in mist and methane, and there were planets that seemed to blur the line between rock and gas, or even planets that may have formed from diamond under crushing pressure. For every new planet found, astronomers realized something even more humbling. Planets are not rare. They are everywhere. The galaxy, it seems, is filled with them. Estimates now suggest that there may be more planets than stars in the Milky Way, hundreds of billions, each orbiting its own sun, each tracing a path through the dark, each carrying with it the potential for something familiar or something entirely alien. To study them, we built eyes that could see across the cosmos. In 2009, NASA launched the Kepler Space Telescope, a mission dedicated to finding exoplanets through the transit method. Kepler watched a patch of sky containing over 150,000 stars, patiently recording their light for years. It looked for those brief, regular dips in brightness, the telltale sign of a planet passing in front of its star. From these tiny flickers, entire worlds were revealed. Kepler's discoveries were astonishing. It found thousands of planets, from scorching giants to rocky Earth-sized worlds orbiting within their stars' habitable zones, the delicate regions where liquid water could exist. It showed us that small Earth-like planets are not rare, but common. The dream of finding another world like our own no longer seemed far-fetched. It became a matter of when, not if. The discoveries reshaped our imagination. Every star we see in the night sky may host its own system of worlds. Some may be barren, others rich in cloud and storm. Some may orbit quietly for billions of years, undisturbed, while others endure chaotic beginnings, collisions, migrations, and fiery transformations. The variety of exoplanets has challenged every model of planetary science, forcing us to rethink how worlds form and evolve. And yet, beneath the science, there is something deeply human in this search. To look for other worlds is to look for ourselves, to wonder whether the story of life is written only on this one small planet, or if it is a chapter repeated countless times across the galaxy.
We listen for the faint signatures of atmospheres, for the glimmer of oceans, for the chemical traces that might hint at biology. Every discovery brings us closer to understanding whether the universe is teeming with life or silent in its vastness. Even now, as new telescopes like the James Webb Space Telescope turn their gaze outward, we continue to refine our techniques. Webb's sensitivity allows us to peer into the atmospheres of distant exoplanets, analyzing their light for molecules like water vapor, methane, and carbon dioxide, the same ingredients that sustain life on Earth. For the first time, we are not just finding planets, we are beginning to explore them, molecule by molecule, photon by photon. Each observation brings a quiet thrill, the possibility that somewhere hundreds of light years away, there might be a world with blue skies and oceans, clouds drifting lazily across a horizon, sunlight glinting off distant waves. It may not be identical to Earth, but it could feel familiar in spirit. Another small oasis in an endless desert of stars. And so, as humanity looks outward, we find ourselves standing at the beginning of a vast new chapter in cosmic exploration. We are learning that the night sky is not a silent emptiness, but a dynamic, living tapestry of worlds, each one turning in its own rhythm, each one part of the grand story of creation. The search for exoplanets has transformed our understanding of the universe, but it has also transformed our sense of belonging within it. We are no longer observers from a single point of light. We are wanderers, explorers, and dreamers, reaching out into the unknown.
The same curiosity that drove us to cross oceans and map continents now draws us to map the stars themselves, to imagine what it might feel like to stand on a world where the constellations are unfamiliar, where two suns rise and set together, where moons shimmer in alien skies. It is a reminder that the universe is vast beyond measure, yet deeply connected, that in every direction there may be worlds turning in silence, waiting for the touch of light, the breath of discovery, the quiet awe of recognition. From the moment a star is born, the seeds of planets begin to gather around it. Every world, no matter how large or small, begins in the quiet swirl of dust and gas that surrounds a newborn star. It starts as a faint cloud within a molecular nebula, a cradle of creation where gravity, over countless years, draws the fine grains of cosmic material inward. The process is both violent and delicate, a balance between collapse and creation. The same forces that crush hydrogen into starlight also sculpt the beginnings of planets from the leftovers. Imagine a young star, only a few million years old, surrounded by a glowing disk. Within that disk, particles of rock and ice begin to collide. At first, these collisions are gentle, almost silent. Dust grains cling together through electrostatic attraction, forming clumps that grow into pebbles, then boulders, and finally, kilometer-sized bodies known as planetesimals. Over time, gravity takes over. These planetesimals crash and merge, forming the first true protoplanets, embryonic worlds orbiting their young star amid the shimmering remains of creation.
This process of formation is universal. From our own solar system to the distant stars that Kepler watched, planets are born through the same quiet alchemy of dust and gravity. But the details vary, sculpted by temperature, distance, and chemistry. Closer to the star, where heat vaporizes ice and drives away lighter elements, rocky worlds like Earth and Venus take shape. Farther out, where temperatures fall and ices can accumulate, the gas giants form, massive worlds like Jupiter and Saturn, whose thick atmospheres are built from the nebula's most abundant gases. The disk itself is ephemeral, lasting only a few million years before the star's radiation disperses it. In that brief cosmic moment, entire planetary systems are assembled, their destinies shaped by countless collisions and migrations. Some planets remain where they formed, others wander, pulled inward or outward by gravitational interactions, sometimes switching places or being cast out entirely into interstellar space. These migrations may explain the strange orbits of many exoplanets we've discovered, hot Jupiters circling perilously close to their stars, or eccentric worlds tracing elongated paths across the darkness. When we study these distant systems, we're not only cataloging their existence, we're witnessing the echoes of creation. Each exoplanet tells a fragment of a larger story: how matter organizes itself, how chaos gives birth to order, how gravity sculpts beauty from dust.
But to uncover these worlds, we must rely on faint signals and patient observation. The distances are too vast for direct imaging, except in rare cases. Most exoplanets are invisible, even to our most powerful telescopes.
Instead, astronomers have learned to listen to the subtle music of starlight, to detect the presence of planets through their influence on the stars they orbit. One of the earliest and most reliable methods is known as the radial velocity technique, the measurement of a star's wobble caused by the gravitational pull of an orbiting planet. As a planet moves around its star, the star itself moves in a smaller orbit in response. This motion causes the starlight to shift slightly toward blue when the star moves toward us and toward red when it moves away. By analyzing these periodic shifts, known as Doppler shifts, astronomers can infer the presence of a planet, its mass, and its orbital period. This method led to many of the first exoplanet discoveries, including 51 Pegasi b. Even now, decades later, radial velocity remains one of our most precise tools. Each star is like a clock, and planets reveal themselves as the tiniest ticks within its rhythm. The second great method, and perhaps the most fruitful, is the transit method. It depends on chance alignment. When a planet passes directly in front of its star, from our point of view, it blocks a tiny fraction of the starlight. The dimming may last only a few hours and reduce the light by less than 1%. But with sensitive instruments, that is enough to reveal an entire world. By observing repeated transits, astronomers can determine a planet's orbital period, its size, and sometimes even its density when combined with radial velocity measurements. If the starlight passes through the planet's atmosphere during a transit, molecules in that atmosphere absorb specific wavelengths of light, creating faint spectral fingerprints.
By studying those fingerprints, we can learn what gases surround that distant planet: water vapor, carbon dioxide, methane, or other compounds that may hint at life-supporting conditions. Other detection techniques build upon the same principles of light and gravity. Microlensing occurs when a planet's gravity briefly magnifies the light of a more distant star, like a cosmic lens. Direct imaging, though difficult, allows astronomers to capture faint glimmers of light from large planets, orbiting far from their stars. Each method contributes a different piece of the cosmic puzzle, revealing worlds in ways that were once unimaginable. As the number of discoveries grew, patterns began to emerge. We learned that small planets, those between the size of Earth and Neptune, are the most common in the galaxy, though our solar system curiously lacks one. We found planetary systems with architectures unlike anything we'd predicted. Tightly packed worlds, orbits tilted at wild angles, stars with dozens of planets locked in delicate gravitational resonances. The more we looked, the more we realized that planetary formation is a dynamic, unpredictable process. Nature seems to favor diversity. There are lava worlds with molten surfaces, water worlds covered entirely by global oceans, and frozen worlds of ice and methane. Some orbit red dwarf stars, faint and long-lived, their habitable zones drawn close around their dim light. Others circle blue giants, whose lifespans are brief but radiant. Among them all, a quiet question lingers: which of these worlds could harbor life? To explore that question, we look for planets within what astronomers call the habitable zone, the region around a star where temperatures allow liquid water to exist.
But habitability is not just a matter of distance. A planet's atmosphere Magnetic field, rotation, and geological activity all play roles in maintaining a stable environment. Some planets may have the right conditions only for a fleeting moment in cosmic time. Others may sustain them for billions of years, as Earth has. The search for habitability is not just about finding another Earth. It's about understanding the range of environments in which life might arise. To do that, astronomers examine exoplanet atmospheres with increasing precision. When starlight filters through a planet's atmosphere during a transit, it carries the chemical signature of the gases it encounters. By separating that light into its component wavelengths, scientists can detect traces of molecules that might indicate biological or geological processes. A hint of oxygen, methane, or water vapor can tell a story, perhaps of volcanic activity, chemical cycles, or even life itself. The data are faint, the signals easily lost in noise, yet each observation brings us closer to understanding the true nature of these worlds. The James Webb Space Telescope has already begun to glimpse the atmospheres of distant planets, analyzing their chemical makeup and thermal structure. Some exoplanets show clouds rich in silicates, vaporized rock suspended in hot air. Others reveal exotic compositions of carbon monoxide and hydrogen. These findings remind us that nature's creativity far surpasses our expectations. In the near future, even more advanced observatories will refine our view. Missions like the European Space Agency's Ariel and NASA's planned Habitable Worlds Observatory aim to study hundreds of exoplanet atmospheres, searching for patterns and potential biosignatures.
With each step, we move closer to an era when identifying a truly Earth-like world may be within reach. Yet, as our technology improves, so too does our sense of wonder. The vast diversity of planets challenges every assumption we once held. It shows us that the formation of worlds is not a rare or miraculous event, but a natural outcome of cosmic evolution, a process repeated endlessly across space and time. If we could see the Milky Way from afar, perhaps we would notice not only its spiral arms and glowing clusters, but also the invisible symphony of worlds moving in rhythm around their stars. Billions upon billions of planets, each shaped by gravity, chemistry, and chance. Some silent and cold, others vibrant and storm-filled. Some perhaps even bearing seas, skies, and the quiet persistence of life. Our search for exoplanets is, in a way, a reflection of our own story. We too are products of cosmic dust shaped by gravity and time, formed from the remnants of stars long dead. When we study the formation of other worlds, we are studying our own beginnings, the same elemental dance that brought forth the earth beneath our feet. And so the exploration continues. Each new world adds to a growing mosaic, revealing how matter becomes meaning, how randomness becomes order, and how from the quiet depths of a collapsing cloud, entire systems of light and shadow emerge. As we drift deeper into this understanding, the universe becomes not emptier, but more alive, a place filled with motion, transformation, and endless possibility.
Beyond the familiar boundaries of our solar system, in the dim light of distant suns, lies a realm of extraordinary diversity. Each exoplanet discovered reveals a new possibility, a new variation on the theme of what it means to be a world. We once imagined that other planetary systems might look like ours, a star surrounded by a tidy arrangement of rocky worlds and gas giants. But the more we look, the more we realize that nature's creativity knows no limits. Every discovery rewrites our understanding, reshapes our expectations, and reminds us that the cosmos is far more inventive than our imaginations. Some exoplanets orbit so close to their stars that their years last mere hours. Their skies blaze with unending daylight, and their surfaces boil in relentless heat. Others drift so far from warmth that they exist in perpetual night, their landscapes frozen solid, their atmospheres quiet and still. Between these extremes lies a spectrum of worlds, each one unique, each one bearing the fingerprint of its own creation. Take, for example, the class of planets known as hot Jupiters. These giants, many times the size of Earth, orbit perilously close to their stars, sometimes so close that their atmospheres are stripped away by stellar radiation. They are tidally locked, with one side always facing the star, baking in temperatures of thousands of degrees, while the other side lies in endless darkness. On these worlds, winds can reach speeds of several thousand kilometers per hour, carrying clouds of molten metal from the day side to the night side. Their skies glow with the eerie shimmer of ionized sodium and silicate vapor.
Rain, if it falls, may be composed of liquid iron. Among them is WASP-76b, a world so hot that iron atoms vaporize into its atmosphere. As its winds sweep from the blistering day side to the cooler night side, the vapor condenses and rains down as droplets of metal. Another, HD 189733b, appears deep blue when viewed in visible light, not because of oceans, but because its atmosphere contains silicate particles that scatter blue wavelengths, glass-like grains suspended in roaring winds. Then there are the so-called super-Earths, planets larger and heavier than our own, yet smaller than Neptune. These worlds are among the most common in the galaxy, even though none exist in our own solar system. Their increased mass allows them to hold thick atmospheres and powerful gravity. Some may be rocky, with continents and oceans, while others could be wrapped in dense clouds or covered in global seas hundreds of kilometers deep. One example is Kepler-22b, orbiting within its star's habitable zone. It may be a warm ocean world, its surface hidden beneath endless water. Another, called GJ1214b, appears to be a mini Neptune, a world enveloped in a thick atmosphere rich in water vapor. Its clouds might glow softly in the infrared, its surface shrouded in mystery. These planets challenge our definitions, existing somewhere between the terrestrial and the gaseous, blurring the line between solid and fluid. Even stranger are the lava worlds, planets whose surfaces are molten, perpetually reshaped by volcanic heat. Kepler-10b, for instance, is a rocky planet that orbits its star so closely that its surface temperature exceeds 2,500 degrees Celsius.
It is likely covered in a sea of magma with silicate vapors rising into a molten sky. Similar worlds like Korot-7b and 55 Cancri E endure the same fiery fate, where each sunrise brings the glimmer of glowing lava fields. But the universe also hosts opposites to these infernos, frozen giants and icy exoplanets drifting at the edge of their systems. Some orbit faint red dwarfs, their suns so dim that the light barely warms their atmospheres. Others wander alone, having been ejected from their systems during violent gravitational encounters. These rogue planets travel through interstellar space, wrapped in the faint heat of their own internal energy, bathed only by the distant light of the galaxy. There are even planets of diamond. The idea may sound like fantasy, but science supports the possibility. Worlds rich in carbon and exposed to immense pressure could form vast layers of crystalline carbon beneath their surfaces. One such candidate, 55 Cancri E, may possess an interior of diamond, compressed by gravity into glittering solidity. To imagine such a place, a planet of shimmering carbon orbiting close to a golden star, is to glimpse nature's extravagance in full. Then there are worlds that defy easy classification, planets that orbit not one but two suns, like those imagined in ancient dreams. These circumbinary planets experience dual dawns and double sunsets, their skies painted with overlapping halos of light. Kepler 16b, the first confirmed example, orbits a pair of stars that dance around one another in an intricate waltz. From its surface, if one could stand upon it, the shadows would be strange and shifting as two suns cast moving patterns across the terrain.
Other exoplanets exist in even more complex systems where three or more stars interact. Some are caught between the competing gravities of multiple suns, their orbits precarious yet stable across eons. To visualize such a world is to imagine skies alive with motion, stars rising and setting in unpredictable patterns, colors blending in the thin atmosphere of a distant horizon. Among the most intriguing discoveries are tidally locked, Earth-sized planets orbiting red dwarfs. These stars are small, cool, and extraordinarily long-lived. Their habitable zones lie close in, meaning that any planet there is likely locked with one face always toward the star and the other in perpetual darkness. On such a world, one side may be forever scorched by light, while the other lies frozen under eternal night. Between them could stretch a twilight band, a region of perpetual dusk where temperatures are mild enough for liquid water. Astronomers call this region the Terminator Line, and it could be one of the most promising places for life to exist beyond Earth. In that twilight world, the sky might glow with the dim red hue of the star, clouds suspended in the faint light, and winds whispering from day to night. It would be a place of balance, neither burning nor frozen, where day and night meet in eternal stillness. The diversity of exoplanets reveals that nature does not follow a single pattern. It creates worlds of unimaginable variety, some that seem familiar, others that stretch the boundaries of what we once thought possible. The more we discover, the more we learn that our solar system is only one arrangement among countless others.
Even our definition of habitability continues to evolve. Once we sought Earth-like conditions, temperate climates, liquid water, a yellow sun. Now we realize that life might find a foothold in far stranger places. It could thrive beneath the ice of a frozen world, warmed by internal heat. It could exist in the dense clouds of a super-Earth, or in the chemical mists of a planet with methane seas. Every discovery opens our minds wider. When we detect a planet's atmosphere rich in carbon dioxide or trace amounts of water, we are not just cataloging data, we are listening for whispers of the possible. Even the harshest world teaches us something about the processes that shape life and the environments that sustain it. Among the thousands of known exoplanets, a few stand out as especially intriguing. Kepler 452b, sometimes called Earth's older cousin, orbits a star slightly brighter than our Sun. It resides in its star's habitable zone, and though it is larger and likely heavier than Earth, its environment may once have been suitable for oceans. Another, called TRAPPIST-1e, orbits a cool red dwarf star, along with 6 siblings, all within a compact system. Several of these planets lie within the habitable zone, raising the tantalizing possibility of multiple Earth-like worlds circling one small ancient sun. The TRAPPIST-1 system has become a symbol of our search, a miniature solar system of rocky worlds, close enough to study in detail, perhaps each with its own unique story. Their atmospheres, surfaces, and climates may all differ, yet together they remind us how fertile the universe is in creating variety.
When astronomers analyze light from such systems, they are not merely observing distant stars, they are touching the boundaries of time. The light reaching our telescopes left those stars years, centuries, even millennia ago. To study exoplanets is to look into the past, to witness the universe as it was long before we existed. Every photon carries information across unimaginable distances, bridging the gap between us and them. Even the faintest data, a small dip in brightness, a spectral line, becomes a window into a world that no human will ever visit. And yet, through mathematics, observation, and imagination, we can reconstruct what these worlds might be like. We can picture their skies, their seasons, their weather. We can imagine the shadows that fall across their mountains or the reflection of twin suns on alien seas. It is this act of imagining that makes exoplanet science both rigorous and poetic. Each discovery begins as numbers, curves, wavelengths, probabilities. But behind them lies the possibility of landscapes, of atmospheres, of entire worlds turning quietly in the dark. And as our technology advances, our ability to see those worlds grows sharper. The James Webb Space Telescope, with its exquisite sensitivity to infrared light, has already begun to analyze the atmospheres of distant exoplanets, detecting the faint glow of their heat. The data reveal not just temperatures and compositions, but weather, clouds forming and dissipating, winds stirring gases across hemispheres. For the first time in human history, we can begin to map the climate of a planet that exists hundreds of light years away. Each observation is a reminder that the cosmos is alive with complexity. Even in places where no life may ever rise, there is movement, transformation, and balance. Storms rage across alien skies, molten rivers flow beneath distant stars, winds sculpt clouds in patterns we may never see. Yet all of it follows the same physical laws that govern our world: gravity, thermodynamics, radiation, chemistry, the universal language of existence. As we learn more about these diverse worlds, we find reflections of ourselves among them. Some may echo the early Earth, shrouded in haze and volcanoes, waiting for life to spark. Others may represent the future, desolate, cooling, and quiet. To study exoplanets is to see the full spectrum of planetary evolution laid out before us, to understand not only what is possible elsewhere, but what has been and will be here. We are discovering that planets, like stars, have life cycles. They are born, they change, and they may die. Some lose their atmospheres to the fury of their stars, others freeze, solidifying into eternal stillness. Yet within this grand cycle lies resilience. Even in the most hostile conditions, nature creates balance, the same balance that allows our own world to persist. The diversity of exoplanets teaches us humility. It shows us that our planet, so comfortable and familiar, is but one variation in an infinite theme. The universe is not centered on Earth or humanity. It is a vast workshop of creation, where worlds are built, destroyed, and reborn across billions of years.
And as we close our eyes to sleep, it is comforting to imagine those distant worlds turning silently in the night, each one a chapter in the story of the cosmos, each one a reminder that the universe is endlessly creative, endlessly beautiful and endlessly alive. Across the immensity of space, there is a quiet question that echoes through every discovery we make. Could there be life beyond our own small world? Every planet we find, every faint flicker of starlight that reveals a hidden companion, draws us closer to that question. The search for exoplanets began as a quest to understand how common worlds like ours might be, but it has become something deeper. It has become a search for companionship in the cosmos. To understand where life might exist, we must first understand what it needs to survive. On Earth, life as we know it depends on a delicate balance of elements and energy. Water, carbon, and light are its foundations. Every living thing on our planet, from the simplest microbe to the tallest tree, is a chemical expression of these ingredients arranged in endless forms. When astronomers look outward, they search for the same signs, not because life elsewhere must be identical to ours, but because these elements are universal. Hydrogen, oxygen, carbon, and nitrogen are abundant throughout the cosmos. Wherever they come together in the right conditions, the potential for life emerges. For that reason, much of the search for habitable exoplanets focuses on one simple factor: liquid water. It is, as far as we know, the most versatile solvent in the universe, capable of dissolving and carrying the chemicals that make life possible.
But liquid water can exist only within a narrow range of temperatures and pressures. Too close to a star and it evaporates into vapor. Too far and it freezes into ice. This delicate balance defines what astronomers call the habitable zone, the region around a star where the conditions are just right for water to remain liquid on a planet's surface. It is sometimes called the Goldilocks zone, a band of warmth and stability where a world might host oceans, rivers, and rain. But habitability is not a simple equation. It is not just about distance. The thickness of a planet's atmosphere, the reflectivity of its clouds, the presence of greenhouse gases, all of these factors can shift that zone inward or outward, expanding or narrowing the conditions under which life might persist. For instance, Venus lies near the inner edge of our Sun's habitable zone, yet its thick carbon dioxide atmosphere traps heat so efficiently that its surface is hot enough to melt lead. Mars, on the outer edge, has lost most of its atmosphere to space, leaving it cold and arid. And yet both worlds may once have had oceans, flowing water, and perhaps even the right chemistry for life. Their histories remind us that habitability is fragile, and that a planet's past may be as important as its present. When we look for habitable exoplanets, we consider these lessons. We search for worlds with stable stars, protective atmospheres, and the right balance of energy. But as our understanding deepens, we find that even the idea of habitability may be far broader than we once imagined.
Life, it seems, is adaptable. On Earth, it thrives in the strangest places, in boiling hydrothermal vents deep beneath the sea, in frozen glaciers, in acidic lakes, even within the rocks themselves. If life can exist there, then perhaps it could exist in equally extreme environments beyond Earth, beneath the ice of a distant moon, or in the clouds of a super-Earth orbiting a dim red sun. Astronomers now think of habitability not as a narrow window, but as a spectrum. There may be planets where life exists on the surface, basking in light, and others where it hides below, protected from radiation and extremes of temperature. Some may have atmospheres rich in carbon dioxide or methane, where microbial life could thrive on chemical energy instead of sunlight. Others might host subsurface oceans warmed by internal heat, as we suspect on the icy moons of our own solar system,
Europa, and Enceladus, where plumes of water erupt from below, carrying traces of organic compounds into space. If such processes occur here, in our cosmic backyard, then they might occur elsewhere too, perhaps in systems where ice worlds orbit red dwarfs, their interiors warmed by tidal forces or radioactive decay. The search for life, then, becomes not just a search for another Earth, but a search for diversity in biology itself. To detect the possibility of life on distant worlds, astronomers study the light that filters through their atmospheres during transits. This light, when split into a spectrum, carries the signatures of gases, fingerprints of molecules that reveal what a planet's air is made of.
Certain combinations of these gases may indicate biological activity. On Earth, for example, our atmosphere is rich in oxygen and methane, a combination that is unstable without the continual influence of life. If such a mixture were detected on another planet, it would be a powerful hint that something alive might be maintaining it. These signs are called biosignatures, measurable indicators that could point to the presence of life. They include not only oxygen and methane, but also water vapor, ozone, nitrous oxide, and other compounds that can be produced biologically. The challenge lies in distinguishing them from abiotic processes, natural, non-living mechanisms that can mimic the same chemical patterns. Volcanic activity, for instance, can produce methane and carbon dioxide. Ultraviolet light from a star can split water molecules, leaving behind oxygen. For that reason, astronomers must interpret these signals carefully, building a context around each discovery. They must consider the planet's size, temperature, star type, and other environmental factors before concluding what a particular gas might mean. It is an intricate detective story, one told in light and shadow, requiring patience and precision. The instruments we have today are beginning to make this possible. The James Webb Space Telescope has already started to analyze the atmospheres of rocky exoplanets, searching for molecules that might suggest habitability. Future observatories, both in space and on Earth, will push even further. They will be able to detect faint glimmers of light reflected from exoplanets directly, separating that light from the overwhelming glare of their stars. In that reflected light lies a treasure trove of information: the color of clouds, the scattering of oceans, the subtle hue of vegetation, if it exists.
Imagine for a moment what it would mean to detect such a signal. A tiny shift in a spectrum could tell us that a world hundreds of light years away has water, or even the chemical breath of living things. The data itself would be simple: numbers, graphs, a curve of light. But the meaning behind it would be profound. It would mean that we are not alone in the processes of biology, that somewhere under an alien sky, chemistry has taken the same leap towards complexity that it did here. Yet, even as we search for such signs, we remain aware that life may not always announce itself in ways we expect. It may not produce oxygen. It may not use carbon. It may not even resemble the delicate balance of DNA and water that defines life on Earth. The universe is old and varied. It may have found other recipes for vitality, other chemistries that work under different conditions. Some scientists imagine life based on silicon instead of carbon, or using ammonia instead of water as a solvent. Such possibilities expand our imagination and remind us that life, if it exists elsewhere, could be both familiar and strange. But even if we never find definitive proof, the search itself is valuable. It teaches us about our own planet, how it sustains life, how it might change, and how rare or common such conditions might be. By studying exoplanets, we learn more about the Earth's uniqueness and fragility. We see how easily the balance of climate and chemistry can be disturbed, how thin the line is between habitability and desolation.
Each discovery sharpens our awareness of how extraordinary our world truly is. When we detect a planet too hot, too cold, too dry, or too volatile for life, we are reminded that Earth occupies a narrow, precious zone, a balance that has persisted for billions of years. And as we look outward, we are also looking inward, seeing ourselves reflected in the grand pattern of nature. The search for life on exoplanets is, in many ways, an act of hope. It reflects a deep human longing, the desire to connect, to find kinship beyond our own sky. For centuries, we have wondered whether there might be others out there, gazing back at us, asking the same questions. Every telescope we launch, every spectrum we analyze, is an extension of that curiosity, a quiet reaching outward into the unknown. In the silence of space, even the faintest signal feels like a whisper, the possibility that life's song might be universal. Perhaps it is rare, a fragile spark that flickers only occasionally in the vast dark. Or perhaps it is common, woven into the very fabric of cosmic evolution, arising wherever conditions allow. We do not yet know which is true, but the act of searching connects us to something larger than ourselves. It reminds us that the universe is not static or distant, but alive with possibility. Every exoplanet discovered, every spectrum studied, expands our sense of belonging. We are not separate observers peering into a foreign cosmos. We are part of it, products of the same matter, governed by the same laws, moving through the same currents of time.
To contemplate habitability beyond Earth is to recognize the delicate miracle of life itself. It is to understand that every world, no matter how barren or distant, carries within it the potential for transformation. Planets evolve, stars change, chemistry unfolds in endless variation. Somewhere, perhaps, those processes have led to consciousness, to beings who look to their own skies and wonder whether they are alone. And so, as we continue to listen and to search, we do so not only for answers, but for connection. In each discovery, there is a quiet message that life is not an accident, but a natural expression of the universe's creativity, one that may bloom wherever there is energy, water, and time. The search for habitable exoplanets is ultimately a reflection of our own desire to endure. It is a story of curiosity, persistence, and wonder, an ancient longing carried forward by modern science. It asks us to look beyond fear, beyond isolation, and to see ourselves as part of a vast, interconnected whole. And as we drift deeper into that understanding, a thought arises, gentle, steady, and humbling. If the cosmos is indeed filled with habitable worlds, then life may be more common than we ever dared believe. Perhaps every point of light in the night sky is not just a star, but a home, a place where oceans move, where winds carry the scent of alien rain, where beings watch their own constellations and feel the same quiet awe that we do. It may take centuries to find the first true signs of life beyond Earth, but the search will continue.
For even if the answer remains elusive, the journey itself enriches us. It teaches us to see with patience, to wonder without haste, to find beauty in the smallest signals. When we close our eyes at night, beneath the same stars that light the galaxy's unseen worlds, it is comforting to remember that we are part of a living universe, one still revealing its secrets, one still creating, one still dreaming of itself through the eyes of those who seek to understand. The study of exoplanets has become one of the most remarkable achievements of modern astronomy. With each decade, we have transformed from speculation to measurement, from imagination to data. Yet even as our instruments grow more powerful, the worlds we study remain distant, their details hidden beneath light years of silence. To know them, we must combine science with intuition, to read the language of light and to imagine what cannot yet be seen. Every discovery begins with a signal. Somewhere in the endless dark, a star flickers, ever so slightly dimmer than before. The change might be no greater than a fraction of a percent, imperceptible to the eye, but to a sensitive detector, it tells a story. A planet is passing in front of its star. The light dips as the planet crosses, then rises again once it has moved on. From this delicate dance of brightness, astronomers can infer the planet's size, its orbit, and sometimes its density. It is a fragile kind of knowledge, built from absence rather than presence. We cannot yet see most exoplanets directly.
Instead, we know them through what they take away: a shadow, a wobble, a pattern in starlight. Yet from those shadows, a universe of worlds emerges. When a planet passes behind its star, a second kind of data appears. The light that once reflected off its surface or atmosphere is momentarily lost, and by comparing that brief dimming to the total light when the planet was visible, scientists can isolate the planet's contribution. That faint glow, once separated from the overwhelming brilliance of the star, contains everything we can currently know about the world itself. Through spectroscopic analysis, the separation of light into its component colors, astronomers can discern the fingerprints of molecules. Each gas absorbs and emits light at specific wavelengths, creating a pattern of lines in the spectrum. Water vapor, carbon dioxide, methane, sodium, and ozone all have unique signatures. When these patterns are found, they tell us what the planet's atmosphere is made of, how thick it might be, how hot or cold the surface could become, and even what kind of weather might shape its sky. Some planets reveal themselves through gravitational tugs, the radial velocity method. As a planet orbits, it pulls gently on its star, causing the star to move in a tiny orbit of its own. This motion creates subtle shifts in the star's light, alternating between red and blue as it moves away or toward us. Measuring this wobble allows astronomers to estimate the planet's mass. When combined with transit data, mass and radius yield density, a clue to composition.
A dense planet may be rocky, like Earth or Mercury. A low-density one may be gaseous, like Neptune. Other techniques rely on the distortion of light itself. Sometimes a planet or a star passes in front of a more distant background star, bending its light through gravity in a phenomenon known as microlensing. The brightness of the background star briefly intensifies, and from that amplification pattern, astronomers can infer the presence of a planet. Microlensing can detect planets that orbit far from their stars, or even rogue worlds drifting through interstellar space without any star at all. Each of these methods captures only fragments, but together they form a growing tapestry of knowledge. The data are often incomplete, the margins uncertain, yet from those faint clues, entire worlds take shape in the human mind. To imagine what these worlds might look like, scientists turn to models, computer simulations that translate physical parameters into visual form. Given a planet's size, mass, and orbital distance, models can estimate its surface gravity, atmospheric pressure, and temperature. If it is tidally locked, one side forever facing its star, we can simulate the contrast between a blazing day side and a frozen night. If it orbits a dim red dwarf, the sky might glow with an amber hue, its sun hanging low, casting long shadows through a dense atmosphere. The process is meticulous yet creative. Scientists adjust variables, run simulations, and compare the results to observed data. They ask questions that reach both the limits of physics and the boundaries of imagination.
What colors would dominate a planet's sky if its air were thick with methane? Would its oceans reflect green light from a different kind of star? How might clouds form on a world where the surface temperature hovers just below the boiling point of water? These visualizations are not mere art, they are tools of understanding. By imagining what light might look like under different conditions, we can better interpret what we see in real observations. A shift in color, a flicker in brightness, a deviation from expectation, each can reveal something about the unseen landscape of a distant planet. Astronomers and artists often collaborate on this work, blending data with aesthetic intuition. Together, they create visual renderings that help the public see what numbers alone cannot convey. In these images, we travel across molten worlds orbiting too close to their suns, ice giants circling in distant shadows, and ocean planets bathed in perpetual twilight. The realism is grounded in science, but the emotion is unmistakable: wonder, curiosity, and awe. One of the greatest challenges in this field is to separate our earth-bound assumptions from universal truths. It is easy to imagine other worlds as versions of our own: blue oceans, green continents, breathable skies. But many exoplanets defy those expectations. Some are far larger than Earth, yet rocky with crushing gravity. Others are mini Neptunes, their atmospheres swollen with hydrogen and helium. Some orbit red dwarfs so closely that their skies might glow crimson, their clouds illuminated by a dim, restless sun. Each discovery forces us to expand our imagination, to think in new geometries of possibility.
A planet might orbit two stars, experiencing dual sunsets like those once dreamed of in science fiction. Another might circle a dead star, warmed by residual heat and radioactive decay. Some may even orbit black holes, their days defined by eternal twilight. As our understanding grows, we begin to realize that no two planetary systems are the same. The architecture of the cosmos is infinitely varied. There are systems where planets orbit in near-perfect harmony, locked in resonant rhythms, and others where gravitational chaos reigns. Planets flung into eccentric orbits, their climates swinging wildly between extremes. From the data, we can infer the dynamics that shape these systems: migrations, collisions, and ejections that sculpt the final arrangement of worlds. In this way, studying exoplanets also tells us the story of cosmic evolution: how dust becomes rock, how rock becomes planet, and how planets create the conditions for atmosphere, chemistry, and perhaps life. The more we study, the more we appreciate the sensitivity of this process. A small variation in a planet's orbit can change everything, shifting it from habitable to hostile, from oceanic to desolate. A slight change in a star's brightness can freeze or boil away water. The physics is exacting, but within that precision lies beauty, a reminder that the same laws that govern distant worlds also shape our own. Telescopes like the James Webb Space Telescope and upcoming missions such as the Habitable Worlds Observatory, LUVOIR, and the Extremely Large Telescope on Earth represent the next step in our exploration. These instruments are designed to capture not just shadows or wobbles, but light itself, the faint glow of an exoplanet, seen directly, separated from its star.
Such direct imaging requires astonishing precision. A star may be 10 billion times brighter than its planet. To see the planet, scientists use coronagraphs and star shades, technologies that block starlight and reveal the faint world nearby. With these instruments, we hope to detect colors and patterns in planetary light, oceans reflecting blue wavelengths, clouds scattering white, vegetation altering the hue of reflected sunlight. Though still a dream, the potential of these observations stirs something deep within us. To see another Earth, even as a pale point of light, would be to glimpse our own reflection across the void. Yet even if we never find a true twin, each discovery is valuable. Every planet expands our understanding of what is possible. Some exoplanets orbit stars so close that a year lasts only a few hours. Others drift alone in the dark, untethered, the remnants of ancient systems. Some may have exotic atmospheres of titanium vapor or molten silicates. Others may be shrouded in clouds of ammonia or methane. There are worlds of glass rain, diamond cores, and metallic hydrogen seas. Each challenges the boundaries of what we once thought planets could be. And in that diversity, we find meaning. The universe is not uniform. It is rich, creative, and endlessly experimental. From the same basic ingredients, dust, gas, gravity, and time, nature assembles an infinite array of outcomes. Some lead to desolation, others to potential habitability, and perhaps a few to life. Our instruments capture their signals, our models translate them, and our imaginations bring them to life.
We visualize what our eyes may never see, guided by light that has traveled for centuries. It is both a scientific act and a poetic one, a conversation between data and dream. The study of exoplanets then is not just about discovery, but about perspective. It teaches us humility, that our world is one among many, our sun one among countless others. It reminds us that even the most precise measurement is only a glimpse, a momentary understanding of something vast and evolving. Each signal, each spectral line, each simulation is a note in the larger music of the universe, a melody composed of gravity, light, and chance. And as we learn to listen more carefully, the harmony grows clearer. To imagine an exoplanet is to bridge two worlds, the known and the unknown. The known comes from data, a planet's radius, its orbital period, the subtle spectrum of its atmosphere. The unknown is everything else, the color of its clouds, the way its winds move, the sound of its storms. Between those two lies a space where science and imagination intertwine. Scientists and artists work together to fill that space with meaning. They take what the numbers suggest and give it form: a sky, a horizon, a mood. And though these images are hypothetical, they are grounded in real physics. A world orbiting a red dwarf star might indeed glow beneath a copper-colored sky, the starlight filtered through a dense, warm atmosphere. A gas giant close to its sun may appear blue or deep purple as molecules scatter light differently under crushing pressure.
An ocean planet might shimmer endlessly, no continents to break its waves, its horizon curving like a perfect mirror around the globe. Visualization is more than illustration. It is an extension of thought. When we render these places, we begin to sense their reality, their weather patterns, their rhythms, their time. We think about how long a day might last, how high a tide might rise, what kind of winds might shape the clouds. Through this process, exoplanets become not just points of data, but places, tangible enough for the mind to visit. In some laboratories, researchers simulate the conditions of exoplanetary atmospheres on Earth. They mix gases in sealed chambers, expose them to intense heat or radiation, and watch the chemistry unfold. By recreating those alien skies, they learn how molecules interact, how clouds form, how light would behave under those unfamiliar suns.
Sometimes they discover surprising parallels, processes that echo what we know from Earth's own evolution. Other times, the results are so alien that they remind us how vast and unpredictable nature truly is. When models and experiments come together, they create worlds that are both foreign and familiar. They teach us that planets are not static objects, but dynamic systems, places where geology, atmosphere, and energy meet in endless dialogue. Volcanoes may sculpt their landscapes, winds may shift continents of dust, magnetic fields may shield them from radiation or vanish entirely, leaving their surfaces exposed to cosmic storms. These forces shape the story of each world, carving its identity over millions of years.
And in these stories, we often find echoes of our own. A world losing its oceans to a brightening star reminds us of Earth's distant future. A frozen planet locked in twilight hints at what our world might have been had it formed farther from the sun. Every exoplanet we study becomes a kind of mirror, reflecting possibilities, futures, and paths untaken. There are teams that specialize in the delicate art of turning scientific data into cinematic experience. They create virtual planets for educational films and observatories, where visitors can drift through simulated skies. These are not fantasies, but reconstructions built from the same physics that governs the cosmos. Through them, we explore what it would feel like to stand on the surface of Kepler 452b, to orbit the double suns of Kepler 16, or to watch auroras dance across a tidally locked world beneath a dim red star. The visuals are mesmerizing, but what makes them powerful is the knowledge that these worlds exist. They are not imaginary, they are real, somewhere out there, their light reaching us across vast stretches of time. In this way, exoplanet science becomes a new kind of storytelling, one that unfolds in numbers, simulations, and dreams. It bridges disciplines, uniting physicists and poets, data analysts and digital artists, engineers and philosophers. It reminds us that discovery is not only an act of measurement, but of meaning. When we look at the faint light from a distant star and deduce the presence of a planet, we are not just finding a rock in space.
We are expanding the human story, rewriting our understanding of what it means to have a home. Every image we construct, every model we refine, adds to a growing atlas of unseen worlds. Some maps are literal, databases cataloging the thousands of known exoplanets. Others are visual, imagined landscapes that help us grasp their diversity. In this expanding atlas, each world holds its own rhythm, its own sense of time. Some complete a year in mere hours, others take centuries. Some are bathed in constant light, others locked in perpetual shadow. Some may orbit in the habitable zone, yet remain shrouded in clouds so thick that their surfaces never see starlight. This variability makes the universe feel alive, a vast experiment in planetary architecture, repeating and reinventing itself endlessly. We see this in the discoveries made by missions like Kepler, TESS, and soon Plato and Ariel. Each telescope has deepened our understanding of what planets can be, showing us that the cosmos is far stranger and more creative than we ever imagined. Kepler taught us that planets are everywhere. Its data revealed that nearly every star has at least one planet, and many have entire systems. In a single patch of sky, it found thousands. It showed us that small planets like Earth are common, not rare. And from that, we learned something profound.
that our solar system is not the exception, but part of a grand, recurring pattern. Tess, scanning nearly the entire sky, continues that search, finding worlds around bright nearby stars where future observatories can probe for life.
Each detection brings us closer to the day when we may see another blue world with oceans and clouds, one that reminds us of home. But even as technology advances, one challenge remains constant: distance. The nearest exoplanet, Proxima Centauri b, lies over 4 light-years away. That may not sound far on cosmic scales, yet for us it is immense. A gulf so wide that even our fastest spacecraft would take tens of thousands of years to reach it. For now, observation is our only bridge. Light is the messenger that connects us, the thin thread that carries knowledge from there to here. And what a messenger it is! Every photon that reaches us has traveled across time and emptiness, carrying within it the memory of a world. When we capture that light, we are catching ancient stories, fragments of other suns, other skies. It humbles us to realize that we can learn so much from so little, that we can build an entire understanding of an unseen planet from the faintest changes in brightness. It speaks to something fundamental in us, the ability to imagine what we cannot touch, to infer the unseen from the seen. That same impulse drove early explorers to map distant lands and sailors to follow the stars. Now it drives us to imagine continents of clouds orbiting stars hundreds of light-years away. In each case, curiosity guides us, pulling us toward the horizon. And as we continue to map the heavens, a new kind of cartography takes shape, one that is not bound to geography, but to light itself. Astronomers speak of spectral fingerprints as if they were landmarks, the faint trace of methane, the subtle curve of a thermal emission, the signature of a hidden ocean beneath clouds. These are the mountain ranges and rivers of exoplanetary science, invisible but no less real. In universities and observatories around the world, teams are preparing for the next great leap, characterizing the atmospheres of Earth-sized exoplanets in the habitable zones of nearby stars. It is a difficult task, demanding not only sensitive instruments, but deep patience. But if it succeeds, we will, for the first time, measure the air of another world, its chemistry, its clouds, its climate. It will be as though we have breathed across light years, sharing a quiet connection with a place we cannot yet reach. For now, our journeys remain within imagination. We travel through simulations, visualizations, and thought experiments. We picture alien horizons and exotic skies, not as fantasies, but as scientific possibilities. And perhaps that is enough, for imagination, when grounded in truth, becomes a form of exploration. It allows us to experience the cosmos, not just as observers, but as participants. Every time we imagine a world circling a distant sun, we bring it a little closer to home. We give it a story, a landscape, a sense of time, and in doing so, we weave it into the larger fabric of human understanding. There is something profoundly peaceful about this act, to know that while we sleep, the universe continues to move, and that somewhere, in the quiet dark, countless worlds orbit their stars in perfect silence.
They do not wait for us. They do not need us, yet we, in our curiosity, reach for them anyway, not to possess, but to understand. It is a gesture of connection, a sign of wonder, a reminder that the cosmos itself is an ongoing conversation, and that through science we are learning how to listen. And so, the study of exoplanets continues. A collaboration across generations and continents, guided by light and patience. With each new discovery, the night sky grows richer. The stars we once saw as mere points of light now carry depth, stories, companions. They are not distant anymore. They are systems, families of worlds, each with its own secrets, each with its own potential for life. In the coming decades, as telescopes sharpen and missions expand, we will see more clearly than ever before. We may find the first true signs of habitability, a planet with a breathable sky, a living biosphere, or the unmistakable scent of life carried through light. Or we may find that life is rare, that Earth is a singular bloom in an otherwise quiet galaxy. Either way, the journey enriches us, for even in absence, there is meaning. To look outward is to look inward, to understand the fragility of our world and the miracle of its balance. The search for exoplanets is, ultimately, a reflection of our own nature, the desire to know, to explore, to dream. We are creatures made of stardust, drawn to the stars. Our questions are the universe asking itself what it can become.
And somewhere, perhaps on a distant shore beneath an alien sun, other beings may be doing the same, lifting their gaze, sensing the faint shimmer of our world, and wondering if they too are alone. In that thought lies a gentle symmetry, a balance between mystery and belonging. The universe, vast and unending, is a tapestry of worlds, each a note in a cosmic symphony. And through science, we have begun to hear the first chords. Their music is soft, distant, but unmistakably beautiful. The sound of worlds turning, oceans glimmering, clouds drifting in eternal silence. If you listen closely, beneath the hum of stars, you might almost hear it. The quiet rhythm of countless planets moving through the dark, each a whisper of possibility, each a dream waiting to be seen. When we look toward the stars and imagine other planets circling those distant suns, we are working at the edge of human perception. These worlds are far beyond the reach of our spacecraft, too distant for even the most powerful telescopes to photograph directly with clarity. Most of what we know about them comes from the subtlest of clues: a flicker of light, a change in brightness, a shift in the color of a star's glow. Yet from those faint signs, scientists have learned to reconstruct entire worlds. It is one of the most delicate and astonishing achievements of modern astronomy, the art of knowing through light alone. Every exoplanet we discover tells its story in photons. As a planet orbits its star, light bends, dims, and scatters in predictable patterns.
A transit, that brief moment when a planet crosses in front of its star, is like a whisper, a fleeting signal encoded with information about size, orbit, and atmosphere. When that light passes through a planet's atmosphere before reaching us, it carries with it a trace of the molecules suspended in those distant skies. By spreading that light into a spectrum, scientists can read the faint chemical fingerprints that mark the presence of water vapor, methane, carbon dioxide, and other gases. This method, called transmission spectroscopy, is one of the quiet miracles of our age. Through it, we can infer the composition of atmospheres hundreds of light years away. We can tell whether clouds or haze might obscure a world's surface, whether its skies are clear or thick, whether it might be too hot, too cold, or just right for liquid water. Each measurement is fragile, often uncertain, yet when combined across many observations, patterns begin to emerge. The beginnings of climate, chemistry, and even potential habitability. It is a process that requires patience and subtlety.
Astronomers must wait for the perfect alignment of planet and star, for a moment that might last only hours and occur once every orbit. They must filter out the noise of the cosmos, the pulsing of stars, the interference of our own atmosphere, the imperfections of the instruments themselves. Out of that noise, they seek a whisper, and from that whisper, they imagine an entire world. But light does not only pass through, it reflects, it scatters, it glows.
Some exoplanets have been studied through the way their light changes as they move behind their stars, an event called a secondary eclipse. When the planet passes out of view, the total light from the system briefly dips again. By measuring the difference in brightness before and after the eclipse, scientists can isolate the faint glow of the planet itself. From that glow, they can infer temperature, albedo, even the heat distribution between day and night sides. It is as if we were listening to a symphony and, through careful attention, could pick out the sound of a single violin hidden among the orchestra. And then there is direct imaging, the most literal and yet the most difficult method of all. Some exoplanets, especially large ones orbiting far from their stars, can be directly observed by blocking the starlight itself, revealing a faint point of reflected glow beside it. The instruments capable of this must achieve precision beyond imagination. They use coronagraphs and adaptive optics, bending mirrors at atomic scales to cancel out distortions caused by our atmosphere. What emerges from that effort are ghostly images, tiny dots that represent entire worlds, glowing faintly in the deep dark. From such delicate data, scientists begin to model these planets, not just their physical traits, but their likely skies, surfaces, and climates. Sophisticated computer simulations take into account the star's radiation, the planet's rotation, the composition of its air, and the circulation of its winds. The models predict how clouds might form, how heat might move between hemispheres, how the light of sunrise might look through alien mists.
One might think of it as a kind of artistic science, a bridge between empirical data and imagination. For when we speak of exoplanets, we are not only describing their orbits or masses, we are also painting them in our minds. Scientists often create visualizations that depict these worlds: oceans glinting under strange suns, mountains rising from violet horizons, storms that circle endlessly under foreign skies. These images are not photographs, but they are built upon mathematics and observation, grounded in physics, yet infused with wonder. In this way, the study of exoplanets occupies a unique place in human thought. It is at once analytical and poetic, rigorous and dreamlike. We measure with precision, but what we are truly seeking is connection, an understanding of what it means to belong to a universe filled with worlds. Every new discovery forces us to rethink what is possible. For example, hot Jupiters, those enormous gas giants orbiting extremely close to their stars, were once thought to be rare anomalies. Now we know they are common, at least in certain kinds of systems. Some orbit so tightly that their years last mere days, their atmospheres heated to thousands of degrees, their clouds made of vaporized metals and silicates. On some of these worlds, it might rain molten glass or iron. They are magnificent and terrifying, testaments to the extremes of nature's creativity. In contrast, there are exoplanets like Kepler-22b and TOI 700d, worlds that lie in their stars' habitable zones, where temperatures may allow liquid water to pool on the surface.
These are the planets that capture our imagination most deeply, for they offer the tantalizing possibility of life. We cannot yet see their oceans or feel their breezes, but through light and calculation, we can sense that they might exist. Places where dawn might break over continents of rock and water,
where clouds might gather and rain might fall, just as it does here. Between those extremes lie super-Earths and mini-Neptunes, categories unknown in our solar system, but common throughout the galaxy. Some of these worlds may have dense atmospheres with thick blankets of hydrogen and helium. Others may be rocky planets with global oceans hundreds of kilometers deep. Some may have no surface at all, only endless layers of cloud. The diversity of planets we've found suggests that nature builds worlds in more ways than we can easily imagine. To study them is to learn humility. Our solar system, once thought to be a typical example, now appears to be only one variation among many. We have planets close to their stars, planets in perfect resonance with one another, planets orbiting twin suns, and planets adrift in interstellar space. We found worlds where a year lasts a few hours, and others where it lasts longer than our entire recorded history. In the quiet of observatories, scientists build instruments that can sense these tiny motions and changes. They design detectors cooled to near absolute zero to reduce background noise. They calibrate their data against the pulsing of atomic clocks. They write algorithms to sift through billions of measurements, searching for that subtle, repeating signal that might mean a planet has been found. And when that signal emerges from the noise, steady, rhythmic, undeniable, there is a kind of reverent silence. Another world has been added to the map of the cosmos. This process is not only scientific, it is deeply human. Each discovery connects generations of curiosity, from the first people who mapped the stars with nothing but their eyes, to the engineers who build telescopes orbiting hundreds of kilometers above the Earth. Each signal is a message across time, saying, "We are still searching, we are still listening." In the coming decades, new missions will carry this search even further. The European Space Agency's Plato mission will focus on finding Earth-like planets around Sun-like stars, while NASA's Nancy Grace Roman telescope will use advanced optics to survey wide fields of the sky. These instruments will refine our view of the galaxy, allowing us to see planetary systems with a clarity never before achieved. But even beyond the technology, the search itself has become a form of reflection, a meditation on our place in the cosmos. To imagine these worlds is to imagine possibility itself. Some may have sunsets that cast colors we cannot name. Some may orbit stars that burn red and dim, stretching out their days in perpetual twilight. Others may exist in endless daylight, their surfaces scorched, their skies filled with shimmering auroras. As the listener drifts deeper into thought, it becomes easy to see how the act of studying exoplanets mirrors the act of dreaming. Both require patience, wonder, and the willingness to let go of certainty.
Both are built on glimpses, hints of meaning that invite us to look closer, to feel more deeply, to accept the mystery of what we do not yet know. And perhaps that is the quiet truth beneath it all. Every measurement, every spectrum, every equation is part of a larger story, one that speaks of human longing, the desire to understand, the impulse to reach beyond the horizon. In searching for exoplanets, we are also searching for the reflection of our own world, scattered among the stars. As our technology reaches outward, so too does our imagination. The data we gather, light curves, spectra, orbital patterns, are mathematical in nature, but they stir emotions that numbers alone cannot hold. Behind every graph, behind every flicker of starlight, there is the ancient human desire to know what lies beyond the next horizon.
To search for exoplanets is to extend that horizon to the very edge of the galaxy, to let curiosity carry us across time and space toward the unknown. In laboratories and research centers, scientists build models of alien skies. They simulate the light of foreign suns, the scattering of particles, the interplay of atmosphere and star. They ask, what color would the sky be on a planet orbiting a red dwarf? Would the light be soft and crimson, casting long shadows through hazy air? Would plants, if they existed there, evolve pigments that absorb that red light, turning their leaves deep shades of black or indigo? These are not idle questions. They are attempts to understand the logic of nature beyond Earth, to imagine how chemistry and physics might give rise to entirely new expressions of life and beauty.
The study of exoplanets, though rooted in equations, inevitably leads to wonder. It reminds us that life, if it exists elsewhere, need not resemble our own. It could emerge from different oceans, breathe different air, feel the warmth of different suns. Astrobiologists study the limits of life as we know it, examining organisms on Earth that thrive in extremes, microbes that live in boiling acid, bacteria that survive beneath Antarctic ice, algae that flourish under ultraviolet radiation. These extremophiles are our messengers, showing us that life can adapt to conditions once thought impossible. When we look to distant worlds, to planets orbiting dim red stars, to moons covered in ice, to gas giants with hidden layers of warmth, we carry these examples as reminders that the spark of life is resilient, persistent, and endlessly inventive. It is strange and beautiful to think that somewhere out there, the chemistry of another world may be unfolding in ways that mirror our own beginnings. Perhaps beneath a foreign sky, molecules are slowly combining in tidal pools or within the clouds of a warm, dense atmosphere. Perhaps a glimmer of complexity is stirring, a moment that, given time, could lead to awareness, to perception, to wonder. This is the quiet hope that moves through every exoplanet discovery. We do not merely seek other planets, we seek kinship. We want to know whether consciousness, or something like it, might have arisen elsewhere. Whether the universe, in its vastness, has dreamt itself into awareness more than once. In the halls of observatories, artists and scientists often collaborate to imagine what these worlds might look like, to give them color, texture, and form.
Some are drawn in soft pastels, others rendered digitally in glowing hues. The artists study the data carefully, the star's temperature, the planet's albedo, the likely composition of its air. They translate those facts into atmosphere, the hue of light at sunset, the shimmer of oceans, the distant arc of moons. Their art is more than illustration. It is a kind of empathy, a way of reaching across space and time to feel what it might mean to exist elsewhere. In these imagined scenes, one can almost sense the stillness of alien mornings, the quiet unfolding of dawn on worlds that will never know our names. One can imagine the patterns of wind sculpting endless dunes, or the slow drift of clouds over mountains carved by forces we do not yet understand. These images invite us to dream, not as escapism, but as expansion. They remind us that the universe is not static, not cold, but alive with potential. Philosophers, too, have joined this conversation. They ask what it means to find another Earth. Would it change our understanding of life, of uniqueness, of purpose? Would it diminish our sense of specialness or deepen it,
showing us that creation is abundant, that the miracle of existence is not confined to a single blue world. Perhaps it would do both. Perhaps the realization that we are not alone would humble us and elevate us at once. It would remind us that life is a thread woven through the cosmos, that the same atoms that make up our bodies once drifted through ancient stars and now form the mountains, oceans, and skies of worlds we have yet to see.
In a sense, this knowledge has already transformed us. Even before we find clear evidence of life elsewhere, the mere possibility expands our consciousness. We begin to see our planet not as the center, but as one note in a cosmic symphony, a single chord among billions. It encourages us to care more deeply for the Earth, to recognize its fragility, to see that the conditions that allow life here are rare and precious. Some astronomers speak of the pale blue dot, the image of Earth captured by the Voyager 1 spacecraft as it drifted toward interstellar space. In that image, our world appears as a faint point of light, suspended in a sunbeam, almost lost against the darkness. Every planet we find beyond our sun is, in a way, another pale dot, another reminder of perspective. Each one holds its own story, its own chance at creation. As the search for exoplanets continues, the technology becomes more exquisite, the questions more subtle. The James Webb Space Telescope can now detect the fingerprints of molecules in exoplanet atmospheres, traces of water, methane, carbon dioxide. Future missions may go further, mapping temperature variations across alien days and nights, capturing direct light from Earth-sized planets. In time, we may detect biosignatures, patterns of gases or chemicals that cannot be explained by geology alone, that hint at the presence of life. If that moment comes, it will be one of the most profound discoveries in human history. A confirmation that the story of life is not unique to Earth, that the cosmos itself is capable of awareness scattered through countless forms across space and time.
And yet, even if we never find that definitive proof, the search itself changes us. It shapes our imagination, unites our curiosity, and deepens our sense of belonging. The pursuit of exoplanets is, in its essence, an act of hope. It is the belief that we can learn more, that the universe is worth exploring, that understanding can bring both knowledge and peace. In the stillness of night, when telescopes turn their silent gaze toward the stars, one can almost feel that connection, the quiet hum of photons traveling for centuries across space, carrying messages from worlds unseen. When that light finally reaches our instruments, it carries within it a kind of music, faint, intricate, and full of meaning. We decode it slowly, patiently, turning patterns into knowledge, knowledge into story, story into wonder. Perhaps that is what astronomy has always been, a way of listening to the cosmos, a way of hearing the echoes of creation and recognizing in those echoes something of ourselves. The planets we find may never be places we can visit, but they are part of our shared inheritance, part of the great unfolding of existence. And so we keep searching. Through the lens of telescopes, through the equations of physics, through the dreams of those who look up at night and wonder. Each discovery, no matter how small, adds a new layer to our understanding of what it means to be alive in a universe so vast, so intricate, so full of possibility. Somewhere, orbiting a quiet star, a planet turns.
Its surface may be shrouded in clouds, its oceans calm beneath an alien moon. The light that leaves it tonight will travel for centuries before reaching us, faint but unbroken.
When it arrives, it will tell us that the universe is wider than we can ever truly imagine, and that even in the deepest dark, there are worlds shining, waiting to be known. And in that knowledge, there is a quiet peace, a reminder that our search for other worlds is also a search for stillness, for belonging, for meaning. We are, after all, the universe observing itself, a collection of atoms that learned to look back toward the stars and wonder what else might be out there, wondering too, perhaps, who might one day look back toward us. The search for exoplanets has brought us to the edge of what we can see, but the future will take us further still. Each new generation of technology brings with it the promise of sharper vision, finer detail, and a clearer understanding of what lies beyond the limits of our solar system. The telescopes of the past revealed that exoplanets exist. The telescopes of the present, like the James Webb Space Telescope, have begun to tell us what those worlds are made of. But the telescopes of the future, now being designed and built, will aim to show us what they look like, and perhaps whether they are alive. One of the next great observatories will be the Nancy Grace Roman Space Telescope, expected to launch later this decade. It will combine wide-field imaging with the power of a coronagraph, an instrument capable of blocking starlight to directly image faint planets around nearby stars.
Roman will survey thousands of systems, searching for exoplanets large and small, refining the census of the galaxy. It will also test technologies that will pave the way for even more ambitious missions that might one day reveal the pale blue light of an Earth-like world orbiting a distant sun. Beyond Roman lies a concept called LUVOIR, the Large UV Optical Infrared Surveyor. It is envisioned as a vast space telescope, many times larger than Hubble, capable of analyzing the atmospheres of Earth-sized planets in detail. LUVOIR would look for the telltale combination of gases that might suggest life: oxygen, ozone, methane, and carbon dioxide, together forming a chemical fingerprint of biology. It would be the first instrument designed not just to find planets, but to seek signs of life itself. Another concept, HabEx, the Habitable Exoplanet Observatory, would pair a powerful telescope with a star shade, a vast flower-shaped screen flying thousands of kilometers away, blocking starlight so the telescope could capture the faint glow of orbiting planets directly. Together, these missions represent humanity's next steps towards seeing the Earths of other suns. The extremely large telescope, now under construction in Chile, will bring the same precision to ground-based astronomy. Its mirror, 39 meters across, will gather light with unmatched sensitivity. It will search for biosignatures in nearby exoplanet atmospheres and measure the conditions on worlds orbiting the closest stars to Earth. Through these efforts, the boundaries of knowledge continue to expand outward. We are learning not only about the planets themselves, but about how planetary systems form and evolve, how dust becomes stone, how gravity shapes orbit, how chemistry gives rise to possibility.
The next great leap will come not from observing light, but from reaching out physically, sending probes beyond our solar system. Projects like Breakthrough Starshot propose using powerful lasers to accelerate tiny spacecraft to a fraction of the speed of light, allowing them to reach the nearest star systems within decades rather than millennia. A fleet of such probes could, one day, fly past exoplanets in the Alpha Centauri system, taking images and measurements as they pass. It would be the first time in history that humanity visits another star. Though these missions remain in the realm of engineering and theory, they show the direction in which our ambitions are moving. We are learning to think not only in the language of observation, but of exploration. The stars, once unreachable, are becoming destinations.
Even as we prepare to reach outward, the data we already have grows richer. Artificial intelligence and machine learning now play key roles in analyzing the immense datasets produced by missions like Kepler and TESS. Algorithms sift through millions of light curves, finding subtle variations that human eyes might miss. Some of the most recent exoplanet discoveries have been made not by astronomers, but by programs that have learned to recognize the patterns of planetary motion. With each discovery, we refine our understanding of how common habitable worlds may be. Statistical models suggest that a significant fraction of Sun-like stars host Earth-sized planets in the right temperature range for liquid water.
If those estimates hold true, then within a few decades, we may have a list of nearby worlds that could support life, not in theory, but in probability. The field of comparative exoplanetology is beginning to emerge, the study of how planetary environments differ and what those differences can teach us about our own world. By comparing hundreds of atmospheres, orbits, and compositions, scientists hope to place Earth in its proper context, not as an exception, but as part of a grand continuum of planetary diversity. And yet, as technology advances, one truth remains constant. The greatest discoveries often lead to deeper questions. Each new exoplanet challenges our assumptions. Each new measurement opens a window into unfamiliar physics and chemistry. Some worlds seem to defy explanation. Too dense, too light, too hot, too strange to fit our models. They remind us that the universe is not obliged to follow the patterns we expect. Still, our progress continues, step by step, observation by observation. The search for exoplanets has become a unifying pursuit, drawing together engineers, physicists, chemists, biologists, and philosophers. It is a field that demands both precision and imagination, one that asks us to balance skepticism with wonder. In time, we may look back on this era as the moment when humanity first began to understand the galaxy as a living system. Not a void of isolated stars, but a vast ecology of suns and planets, each interacting, each evolving, each offering clues to the deeper story of creation. For now, we continue to listen, to the faint signatures in starlight, to the distant rhythm of worlds turning unseen. The future of exoplanet science is one of patience and persistence, guided by the belief that understanding brings meaning. And as we refine our instruments and extend our reach, we draw closer to the moment when we will look upon a distant Earth and see, reflected in its light, the same mystery that surrounds our own. The future of exploration is not about leaving home, but about expanding our sense of what home means. Each discovery reminds us that the universe is filled with potential, and that our search for other worlds is, in the quietest way, also a search for ourselves. The study of exoplanets began as a question, a simple wondering that reached beyond the stars we could see. For most of human history, the idea of other worlds was a dream suspended in imagination, untethered by proof. But now, that dream has become one of the most extraordinary scientific realities of our age. We have confirmed thousands of exoplanets and suspect billions more. The discoveries have come from light, from motion, from the delicate interplay of physics and time. Each planet we find teaches us something new about the diversity of the universe, about the history of our own solar system, and about the fragile conditions that make a world habitable.
Later came the discovery of super-Earths and mini-Neptunes, planets that filled in the gaps between the familiar categories of our own solar system. With them, our models of planetary formation evolved, embracing chaos and chance as fundamental parts of cosmic architecture. We learned that stars form within clouds of gas and dust, that disks of material orbit them and condense into worlds. Collisions and migrations sculpt these systems, moving planets inward or outward, shaping orbits that may remain stable for billions of years or spiral toward destruction. Planetary systems, like living organisms, are dynamic, born from turbulence, refined by gravity, and aged by time. Through spectroscopy, we began to decode the atmospheres of exoplanets, reading in their light the chemistry of air, the traces of clouds, the scattering of molecules. From these signals, we learned that some worlds are wrapped in thick hydrogen blankets, others in misty carbon dioxide, and some are stripped bare by radiation. We learned that temperature, distance, and stellar type intertwine in intricate patterns that define whether a planet is frozen, scorched, or balanced between extremes. And then came the question of life, the quiet, guiding thread that runs beneath all exploration. The habitable zone, that narrow band around a star where liquid water can exist, became our compass. It is not a promise of life, but a condition that makes life possible. Around red dwarfs, that zone is close and precarious, subject to flares and tides. Around hotter stars, it stretches outward, fragile and fleeting. Yet within these bounds, we have found worlds that could, in principle, bear oceans and atmospheres like our own. We are learning to search for signs of biology, not by sight, but by pattern, by the chemistry of imbalance.
On Earth, life alters the air. Oxygen, methane, and carbon dioxide coexist in ratios that cannot be explained by physics alone. When we look to distant worlds, we seek those same contradictions, fingerprints of metabolism, the subtle echoes of living processes. The science is careful, patient, and humble. It acknowledges the limits of our perception, the ambiguity of data, the distance that separates us from certainty. Yet even within those limits, we find meaning. Each new discovery refines the probability of life beyond Earth. It tells us that the universe is not empty, but fertile, that planets form naturally wherever stars are born, that the seeds of habitability are scattered generously through space. From this foundation of science, the reflection deepens. We begin to see the search for exoplanets not merely as a technical pursuit, but as a mirror held up to ourselves. In learning about other worlds, we learn about our own, its fragility, its rarity, its improbable balance. Earth, seen in the context of the galaxy, is both ordinary and precious. Its orbit, its atmosphere, its magnetic field, its oceans, all are products of chance, yet together they sustain life. The study of exoplanets reminds us that balance is delicate, that habitability is a narrow thread woven through the tapestry of the cosmos. It makes us aware that our world, though small, carries a significance beyond measure. It is a vessel of consciousness, a point from which the universe can look back upon itself. And as our understanding grows, so does our sense of connection.
Every star we observe is a potential home. Every faint signal, a whisper of possibility. The distances are vast, but the physics is shared. The same elements, the same forces, the same laws shaping every world. Carbon, oxygen, nitrogen, hydrogen, the building blocks of life, are universal. The atoms in our bodies were forged in the same processes that build planets and stars. To study the cosmos is to recognize ourselves as participants in its unfolding. The next chapters of exoplanet science will be written with tools we are only beginning to imagine. We will detect smaller planets, cooler planets, planets with thin, breathable atmospheres. We will measure the colors of their clouds and the glow of their seasons. We will model their climates and perhaps identify one, a small rocky world orbiting a quiet star that shows the unmistakable signature of life. That moment will not only be a scientific milestone, it will be a philosophical one, for it will mean that life, the phenomenon we once thought confined to this single blue sphere, is part of the fabric of the universe itself. It will mean that we are not alone, that somewhere out there, across the darkness, another world breathes. Yet, even if that day never comes, the search itself is enough. The act of looking outward, of listening for other worlds, is an expression of the same curiosity that defines our species.
It connects the first humans who gazed at the stars with the scientists who guide telescopes today. It speaks of hope, a quiet, enduring hope that knowledge leads to understanding, and understanding leads to peace. When we look at exoplanets, we are not only charting distances and orbits, we are contemplating existence. We are acknowledging that the cosmos is vast enough to hold infinite variation, and still intimate enough to touch something deep within us. The light from a distant planet may take centuries to reach us, yet when it does, it arrives as something familiar, a reminder that we are part of a shared creation. Imagine for a moment standing on one of those distant worlds. The air might be thinner, the gravity stronger, the stars brighter. Perhaps two suns rise together, or a ringed gas giant fills half the sky. The constellations would be different, but the feeling of wonder, the awareness of being small beneath the infinite, would be the same. That feeling, universal and timeless, binds all observers wherever they may be. It is possible that life elsewhere would not look like us or think like us. It may perceive the universe through senses we cannot imagine. Yet, if it exists, it too would look upon its sky and wonder. It too would feel the pull of curiosity, the desire to understand the mystery of its own being. In that shared wondering, across light years and epochs, there is connection. The search for exoplanets is therefore not only a scientific endeavor, it is an act of continuity. It is the universe exploring its own structure through us, through our instruments, our thoughts, our dreams. The same laws that govern the motion of distant planets govern the beating of our hearts. The same starlight that illuminates other worlds has crossed the atoms of our eyes. And as the night deepens and the stars emerge, we can sense the rhythm of that unity, the quiet pulse of existence, steady and vast. Each exoplanet we discover is another verse in the cosmic story, another reminder that creation is ongoing, that the universe is still unfolding, that there is more to know than we can ever reach. In the end, the study of exoplanets brings us back to silence, the kind of silence that invites reflection. We realize that we are both the observer and the observed, both the question and the answer. Our instruments may detect the faintest flicker of light, but it is our imagination that gives it meaning. We translate photons into landscapes, data into dreams. Somewhere tonight, a planet circles a star, unseen and unknowing. Its orbit is steady, its surface quiet, its atmosphere shifting under alien winds. The light that leaves it now will travel across space, passing through clouds of dust across the gulf of centuries, until one day it touches a detector on Earth. In that moment, across all that distance, a connection is made. The smallest bridge between two worlds. And perhaps that is what all science is, the building of bridges between what is known and what is possible.
Each bridge begins with a question, and each question carries us a little farther into understanding. The stars above us are countless, but the curiosity that drives us toward them is singular. It is the essence of being human. So we keep listening, we keep watching. We trace the patterns of light and motion, knowing that within them lie not just facts, but meaning. For every world we find reminds us that the universe is rich beyond measure, and that even in its vastness, we belong to it completely, quietly, beautifully. As the stars turn slowly overhead and the night drifts toward dawn, that thought becomes a kind of peace. The galaxies continue their slow dance, the planets their endless orbits, and somewhere across the deep stillness of space, light continues its journey home.